Here's yet another example where we can apply the law of conservation of angular momentum. So there's a rubber ball, and the rubber ball is traveling at 10 meters per second toward this uniform rod, and the rod has a length of 4 meters and a mass of 5 kilograms. So the ball hits and collides inelastically with the rod. So it doesn't stick to it. It's not perfectly inelastic. And I think we'll prove in this problem that it's not elastic either. In other words, some mechanical energy is wasted away as thermal energy. Here's what we need to figure out. The ball is going to hit the rod, and so this is what the system looks like afterward. The rod was originally in this position when the ball first hit it, but the ball hits off center, and so that the collision provides a torque that makes the rod rotate about its center of mass. So the rod gains some angular speed, which we have to calculate, but the rod also projects forward in this collision, so the speed of its center of mass is also unknown. And then we'll just make up some values and say, hypothetically, what if the ball came bouncing back off of the rod and its speed is not 10 meters per second as it comes back, the speed is only 2 meters per second as it comes bouncing back. So, given all this information, can you figure out both the final angular speed of the rod and the final speed of the center of mass of the rod? So what's conserved in this collision? If the collision really is inelastic, then mechanical energy is not conserved. Now, I believe that linear momentum will be conserved in this case because there are no external forces acting. So this is different than the previous examples we've had. We've seen a couple other examples where the object that the ball collides with is mounted on some axle, and there's a external force between the axle and the rod, but this rod isn't mounted on any axle at all. It's just free to rotate through space. So there are no external forces. There's an internal force, and that internal force is the force of the collision, but that's a force that's shared between the ball and the rod, so it's internal. So linear momentum is conserved and angular momentum is conserved. Well, because both of these quantities are conserved, then we're going to end up with two equations that express both of those conservation laws, and with two equations we should be able to solve for two unknowns. So let's apply the law of conservation of linear momentum. It tells us m1u1 plus m2u2 has to equal m1v1 plus m2v2. Okay, we'll label these. Object number 1 is the ball, and object number 2 is the rotating rod. So there is no initial velocity for the rod. So let's see, m1, what's that? That's our 3 kilogram ball. u1, that's 10 meters per second. And then v1 is 2 meters per second. Ooh, careful. It points in the other direction. It's negative 2 meters per second. m2, that's the 5 kilogram rod, so we have to solve for v2. So it looks like v number 2 would be equal to m1u1 minus m1v1 all divided by m2. So the velocity of the center of mass of the rod is equal to the mass of the ball times the difference between its initial speed and its final speed, all divided by the mass of the rod. So that means it's equal to 3 times 10 minus negative 2, all divided by 5. So this is equal to 36 fifths. So it looks like the velocity of the center of mass of the rod is equal to 7.2 meters per second. Okay, let's see if we can find the angular speed of the rod. Angular momentum is conserved. Initial angular momentum equals final angular momentum. So the initial angular momentum is all due to the rubber ball acting as a point mass. So this is mv, well, careful. Let's stick with our nomenclature here. This is m1 u1 r perpendicular. And then that's equal to, let's see, final angular momentum is twofold. It's the angular momentum of the rod, which acts as a rigid body, plus the ball comes bouncing back and has angular momentum as a point mass. So this is plus m1 v1 r perpendicular. What's r perpendicular? So that's the distance between where the rubber ball hits the rod and the axis of rotation. So the rod ends up rotating about its center of mass. So this distance is r perpendicular. So let's see, we were told the rod is 4 meters in length, and then it was just given that the ball's hitting at 3 meters from the end. So the distance between the center of mass and the location where the ball hits would be 1 meter. So that's our r perpendicular value. Okay, so r perpendicular is 1 meter. M1 is 3 kilogram. U1 is 10 meters per second. M1 is 3 kilogram. V1 is negative 2 meters per second. Okay, so I, what's I? This is a rod rotated about its center, so I is equal to 1/12 ml squared. All right, so let's see, rearrange the equation. Omega is m1 u1 r perpendicular minus m1 v1 r perpendicular, all divided by rotational inertia. We can factor out the m and the r perpendicular. So this is m1 r perpendicular times u1 minus v1, all divided by 1/12 capital M L squared. Okay, plug in the values. This is 3 times 1 times 12, all divided by 1/12 times 5 times 4 squared. Is this mental math? Let's see. Dividing by 1/12 in the denominator. All right, might as well multiply top and bottom by 12 to cancel that out. 12 times 12 is 144, so this is 3 times 144 divided by 5 times, what's 4 squared? 16. Okay, so the 3/5 part we'll leave alone. 144 over 16 is the same as 72 over 8, is the same as 36 over 4, is the same as 18 over 2, is the same thing as 9. Okay, so 3/5 of 9 is the same as 27/5, which gives us 5.4 radians per second. No, all right. So we did it. We found the final speed of the rod's center of mass, and we found the final angular speed of the rod. Now let's just make sure that this is a reasonable result. We know that the final kinetic energy has to be less than the initial kinetic energy because the initial kinetic energy was converted into the final kinetic energy plus some Q value. So our initial kinetic energy, let's see, what would that be equal to? That's just due to the initial speed of the rubber ball. So 1/2 mv squared. 1/2 times 3 times 10 meters per second squared. So 10 squared gives us 100. 3 times 100 gives us 300, and half of that would be 150 joules. All right, what about the final kinetic energy? Well, that comes in 2 parts. The final kinetic energy is the rotational kinetic energy of the rod plus the translational kinetic energy of the ball that comes bouncing back. So let's figure out this part. This is 1/2 times 3 times -2 squared. So that gives us 4. 1/2 of 4 gives us 2, and 2 times 3 gives us 6 joules. So we've got that. Let's find the rotational kinetic energy of the rod. 1/2 I omega squared. So 1/2 times 1/12 ml squared times omega squared. But wait a minute. We know omega is 5.4 radians per second. So 5.4 squared. So what's this? Let's see. That's going to be 1/12 times 5 times 4 squared. So I believe that comes out to 6.67. Okay. So 1/2 times 6.67. Let's see, what's 5.4 squared? I think 5.4 squared gives us 29.16. You can verify these values on your calculator. So when you multiply all this out, you get 97.2 joules, and we have to add to that these 6 joules. So we get a total final kinetic energy of 103.2 joules. Well, that's reasonable. 103.2 joules is something less than 150 joules, so we can figure out what the Q value is. Our Q value is 150 joules minus 103.2 joules, which gives us, what is it, 46.8 joules of wasted energy. Okay, so now that we've seen a few examples of the law of conservation of angular momentum, the last topic of study is gyroscopic motion. So feel free to move along and finish Unit 4.2 on rotational dynamics by investigating gyroscopic motion and a behavior known as precession.